All right, all chemists need to be able to balance chemical equations. I'm combining two problems here, taking a look at A, B, C, and D for the balancing purposes. Um, Basic strategy, we know that the number of atoms on each side of each element have to be equal. Also note that we can't change the subscripts here. That would change the chemical identity of the compound or the element. So keep that in mind as we're balancing. We can only add coefficients. We also, it's not imperative that we do this because the equation and the stoichiometry would still be valid. But as a general rule, chemists like whole numbers here in front of each formula. So keep that in mind as we proceed. So let's take a look at the reaction of sulfuric acid and aluminum to produce aluminum sulfate and hydrogen gas. You should know how to write out each formula here because you memorized sulfuric acid and hydrogen gas, and aluminum sulfate is, of course, ionic. As a general rule, we want to pick out an element that only appears once on both sides. So we might start with the aluminum here. We see that we have one aluminum on the left and two on the right, so we can achieve balance by adding a 2 in front of the aluminum. As a good rule too, we can also group polyatomic ions. So notice that there are sulfates. So instead of balancing the sulfur and the oxygen independently, we can balance them as a group in terms of the sulfate unit. So we have one sulfate on the left, 3 on the right. So we can add a 3 in front of the sulfuric acid. Now we have 3 sulfates on the left and 3 on the right. So that's good. Finally, let's balance the hydrogen. Notice we have to distribute the 3 to the 2 to get 6 hydrogen atoms on the left. We have 2 on the right, so we can balance the hydrogen by adding a 3 in front of the hydrogen gas. Remember, you can always check your work by counting the number of atoms, so that should be good. Let's move on to the next one. So we have the reaction of P4O10 with water. Here I don't see any polyatomic ions, and again we want to pick an element that only appears once on both sides. So I wouldn't pick oxygen to start this balancing because it appears twice on the left-hand side of the arrow. So let's either start with phosphorus or hydrogen. We picked phosphorus here. Doesn't really matter what you pick, but it turns out to be a little easier with phosphorus because you can avoid fractional coefficients. So we notice that we have 4 phosphorus on the left, 1 on the right, so we're going to multiply or place a 4 rather in front of the phosphoric acid to get 4 phosphorus atoms. We're next going to turn our attention to the hydrogen. Now we have 12 on the right and we have 2 on the left, so we can put a 6, excuse me, in front of the water to get our balance. And finally, counting the number of oxygen atoms, notice that we have 16 on the left, and we also have 16 on the right. So conveniently that works out, and this reaction is balanced. Okay, let's move on to the 2 more difficult ones, hydrogen peroxide going to water and oxygen gas. Let's pick hydrogen. Again, we wouldn't want to pick oxygen to start off with because it appears twice on the product side. Hydrogen obviously is balanced. We have 2 on each side. However, notice that the oxygens are a little confusing, and they're confusing because we have a total of 3 on the right and 2 on the left, and 1 is odd and 1 is even. So the question is, what do we do? And we can alter this by adding a fractional coefficient. So if we have 1/2 of a O2 molecule, that will contribute 1 oxygen atom. Now, obviously, there's something inherently less than satisfactory about having half an oxygen gas molecule. So typically what chemists do is they multiply to get whole numbers. So we can multiply the entire equation by 2 to get 2 hydrogen peroxide, 2 waters, and an oxygen gas molecule. And generally you would omit the 1 in front of the oxygen gas, but we're showing it explicitly for clarity. Okay, let's take a look at the combustion of heptanol. Whenever you have a combustion reaction, remember that the other reactant is O2, and you produce carbon dioxide and water. You'll learn some exceptions to this in AP chemistry, but for now, let's assume that the other reactant is O2 gas, and the products are carbon dioxide and water. We're going to go through our same analysis. So I wouldn't want to start off with oxygen here because it appears twice on the left and twice on the right. So let's start with carbon. So let's put a 7 in front of the carbon dioxide. Hydrogen would come next. Notice I have 16, and the hydrogens here are, they're written differently because it's implying something about the bonding that we'll talk about later, but you shouldn't think of them as being chemically different because they're atoms of hydrogen. But we have 16 on the left, 2 on the right, so we're going to put an 8 in front of the water to balance that out. Now the hard part comes with the oxygen. So notice we have 14 plus 8 from the water for a total of 22 oxygen atoms. Normally that would be okay, but don't forget we have 1 oxygen atom on the left. So if we have 1 oxygen atom in heptanol and an O2 molecule, the question is what do we put in front of the O2 to generate 22? And the answer is we need 21 oxygen atoms to combine to give us, with the 1 to give us 22, so we can multiply by 21 halves. Again, we don't want fractional value, so we're going to multiply everything by 2. We want whole numbers. Generally, that's how chemists like to think about reactions in stoichiometry. So we would get 2 heptanol molecules, 21 O2, 14 carbon dioxide, and 16 water. And if you can do this one, you can probably do some of the more difficult problems we could give you on the test. Good luck.